How many axial positions are on one side? 1, 2, 1, 2, 3, and 1, 2, 3. These 3 hydrogens, or these 3 groups that are here, are on the same side, and they are very close to each other in space. That is called a 1,3 diaxial interaction. Whatever groups are there will feel 1,3 diaxial interaction, no matter what they are. But the bigger they are, the more 1,3 diaxial interaction they feel. Yes? So you always want to place the biggest group in the equatorial position, so it does not feel 1,3 diaxial interaction. So there's 1,3 diaxial interaction there, and is there more 1,3 diaxial interaction?
Yeah.
Yes, there is, for the 3 that are on the bottom, which are these 3. So there's 3 on the top and 3 on the bottom. So whatever group is axial will always feel 1,3 diaxial interaction. Is that clear? So what do you always want to do? You always want to have the largest group in the equatorial position. And you go from axial to equatorial by doing what?
A chair flip.
A chair flip. In here, you have 1 in the axial. What does this one feel? 1,3 diaxial interactions, yes? Yeah. Not good, it doesn't want to be here. But if it does a chair flip, then this happens. And another group, 1,3, feels diaxial interaction again. Are these both the same? They are the same. I mean, they're not the same, but they do feel the same 1,3 diaxial interaction, so they are the same in strength. So let's do the other one. Okay? What was it? What was it that we had written here?
You wrote
okay.
1 ethyl, 3 methyl.
Trans.
Yeah.
Trans. 1 ethyl. 3 methyl. And if you have to draw them, see if you're careful that when you do the chair flip, they are both easy to read. If you can, actually, you want to do 1,4 instead of 1,3?
What's the difference?
What's the difference? I don't know. Why did you find out?
Butane versus propane.
Butane versus propane? No, that's not the same. Okay, do 1,3. That's what we wrote. Now let's do 1,4. Yeah, some of you complained. No. Too much work for you. Do whatever you want. I'm going to give you on the test 1,4. So I thought maybe it was good if you practice, but no, you complained, so let's forget it. No, not you. Somebody else went like this.
Can we do both?
Yeah, you can do both. So what do you want to do? You want to do 1,4?
Yeah.
Both.
1,4, you sure?
Yeah. Yeah.
Okay, let's do 1,3. Okay, let's do 1,4. Peak is pointing up. Pointing up. That is a chair 1,4. What do you like to choose for this 1,4?
The right side.
Huh? You want to choose this one? This one? Okay. What do I put in what place?
I think carbon number 1.
This is going to be carbon 1, yes?
Yeah.
What am I going to put here? An ethyl. Am I going to put it up here or down here?
Up.
Up? Put it up? Okay, fine. We can put it wherever you want. It's okay. So that's the ethyl. 1, 2, 3, and 4. Okay. So this here will be a methyl. This is what type of bond? This is the upper bond. And it needs to be trans. So the next will be what type of bond?
Equatorial.
Lower bond.
No.
Lower bond.
Nothing to do with equatorial. Nothing at all to do with equatorial. If this is the upper bond, the next one is going to be the lower bond. Which one is the lower bond from these two? This one? Yes?
Yeah.
Does it like to be like this?
No.
Now this will feel what?
Diaxial.
1,3 diaxial interaction. And this is also going to feel 1,3 diaxial interaction. So this is very bad. Looking very bad. So this is going to do a chair flip. We can say something like this.
I have a question. It's 4-methyl because it's on the 4th carbon.
Yeah.
So why did you rotate to the left, not to the right? Like, why did you start counting?
What?
Why did you count?
1, 2, 3, 4.
Oh, never mind.
Where did I write 6?
Okay, sorry. I have a question too.
Where do you see 6?
Where is this? If we know that the biggest group needs to, because of 1, 3 interaction or whatever, then we prefer for it to be an equatorial, and it's trans, so you can basically choose which one goes upper or bottom. Like, why didn't we just think about it beforehand and do a lower bond, which happens to be an equatorial bond, instead of having to go through the chair?
Because you do not control the brain of other people. You only control yours. So if you would have chosen to put it in equatorial, that's okay for you.
A lower bond that happened to be.
It doesn't matter because you're going to have to do a chair flip nonetheless.
Okay.
So you're going to have to draw this one either way. And
Okay.
you're going to have to draw the other one either way.
Okay. But we do chair flips so that it lands more
No, we do
convenient?
not do chair flips so they land where we want it to land. We do chair flips because that's what they do.
Okay.
So this was this way. Now this one will be the other way. Now remember, you got to draw these on the test, so it really doesn't matter where you begin. If you want to begin from the least stable, that's what we did here. That's what she was saying. You begin with the least stable, then the next one is going to have this equatorial. You can begin however you want. But here's a chair flip. And if you did this chair flip, where is this carbon at now?
Down.
This is this carbon. And it was axial before, now this group will be equatorial. CH2, CH3. The next group was axial before, now is this carbon, yes? What is it, axial or equatorial?
Equatorial.
Equatorial. And now we make sure we did this right. This is upper bond or lower bond? This is the upper bond. And if it is the upper bond, then this needs to be what in order to be trans?
Lower.
And lower bond. So this is what we have, upper bond, lower bond. This is trans. Which one is more stable?
The second one.
The second one is more stable, so you are going to write on the test when I ask you, most stable. And the explanation is, and explain, will be because largest group is in the equatorial position. And this is what? This one here is the least stable. Because
The largest group is in the axial position.
Diaxial.
because
The largest group is in the
Three.
axial position.
Yeah, but more specifically,
One
third.
the largest group
Is on
feels
feels more
Steric
steric.
1,3 diaxial interaction. How did you like that?
That's good.
You said that's better?
Yeah, I feel better.
Yeah.
You feel better? No, the book is verbose, yes?
Is what?
Verbose.
Very.
What do you mean?
The book goes blah, 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 blah.
Yeah.
The book has a lot of writing on it, yes?
Yes. Very long. Oh my
The book is
God.
on fire.
I got that one by David Klein.
Okay.
I meant Calvin Klein.
Yeah. Yeah, no, they got good genes, man. You know what they say, snitches get stitches. Okay, why don't we do 1-3 then, since I don't want to disappoint some of you and not do 1-3, yes?
Can we do like the 6 one?
What happened?
The 6?
Huh?
The 6?
Can we do the cis? Why you want cis? You just want to try all possible combinations? No, I gotta save some for the test.
That's not fair.
It's okay, I got the power. Not about being fair. It's not well, not so much that, but. Okay, you try to do it. You got 1 minute. What happened? Are we gonna try the cis? No. We're done with this one. After this one, that's it. We did cis last week, and at the beginning of today. Guys, you are learning this, yes? You follow the rules I'm giving you. It doesn't matter if it's cis or trans. You don't have to try everything.
When we're redrawing it, do we have to draw all the equatorial and axial lines, or can we just draw the ones that are relevant, or?
You can draw the ones that are relevant. La Vista, you sleeping in my class? What's wrong with you? I'm gonna tell La Vista. Okay, let's draw it. Yes? I draw all of these for practice, yes? We get used to looking at it and drawing them. 1,3. Where are we gonna do this?
On the top.
Huh?
One
On the top right.
we start at the bottom.
You wanna start here?
Yes.
You start here, it's gonna end there.
Can we start at the bottom and
start
then end
here,
at the other bottom?
It's gonna
Yeah.
end here.
Yeah, let's do that.
Okay.
That's easier.
Wait, can you go the other way?
You wanna start here and go here?
Yeah.
Yeah, we can do whatever you want.
Either one.
That's what you want?
Yeah.
Okay. What do I put here? Ethel. You want it here axial. You want it axial?
Yeah.
Doesn't matter if you want it axial or equatorial. And if this is 1, 2, 3.
Yeah.
There it is. I am going to put what here? Methyl.
The methyl.
Here?
CH.
No.
No.
Why
It
not?
should be on the lower
You
bond.
have to put on the lower bond.
Yeah.
So this is the upper bond. This needs to be in the
Lower
lower
bond.
bond so it can be trans.
Right.
So here?
Yes.
Yes.
Very nice. And now
Sure.
I am going to do a chair flip.
Sure.
And did I say that the chair flip goes through the boat conformation? In order to do a chair flip, it has to go through the boat conformation. Did I show you the boat?
Yeah.
I don't remember.
Yes, you did.
You should. Yeah.
So now this time, I am going to draw that one that way. Yes? This carbon is which carbon? This carbon.
That one.
That used to be axial, and now it will be equatorial. And this was equatorial, now will be axial. Which carbon is that going to be?
That one's
In the middle.
going to be.
This one?
No.
No.
Here.
Yeah.
This one? Oh, I shouldn't put a period on it. That's gonna be this one, because that one went up, this one goes one that way. Well, it looks to go that one that way, but if you can see it, I mean, it's not like it really goes anywhere, right? You just bring this up, that kind of stays there. You just bring this up, that stays there. It just looks like it one that way. So this was equatorial, now will be axial.
Axial.
So it's here.
At the bottom.
I don't know, is that trans? You sure? What bond is this?
Upper.
Upper bond, and this is?
Lower.
Lower bond, okay, that's trans. So which one of those two is the most stable? Which one?
The one where the bigger group is in the equatorial position.
This is the most stable. Most stable. Because the biggest group is equatorial.
position.
This, most stable, because this is equatorial. And this is the least stable because
It feels a
Least
1-3
stable.
diaxial
because
interaction.
this has 1-3
diaxial.
diaxial interactions.
Do you want us to circle?
No, I'm just saying, I don't have to write this. This, by the way, does this feel 1-3 diaxial interactions too?
Yes.
Of course.
Just left.
But this group is a little bit smaller than that group. So this should feel more 1-3 diaxial interaction than this one. So that's why the equilibrium will lie where? To the right or to the left?
To the right.
To the right, so we can draw a big arrow that way and a smaller arrow going the other way.
Why is that again?
Because the equilibrium will lie to the right. Now another way of drawing these things, because it looks like it is not over yet, yes? If I were to do this, have I shown you here dash and wedge before? We have, yes? Another way of drawing this is if I draw something like this here and something like that there. This means what? This is coming this way,
Towards you.
and that means it's on the other side. So if I am going to redraw this, because if one is cis or trans and I want to draw it like this, I can't just draw this. Can't draw this anymore, yes? This is trans 1,3. Here is ethyl, and I can't draw the 3 here like that. That's not okay anymore. Yes? Is that okay? It's not, because this doesn't show you cis and trans. That shows you cis and trans, or this shows you cis and trans. So if we're going to make this cis, we're going to place the group where? Where do you want to place it here? We lost the equatorial on the axial here. Where do we place it?
Opposite.
Where do you want to place it? Choose. In the wedge or the dash? You like wedges first, yes? Let's put it here. No, actually, yeah, I'm depressed. I don't know what to decide. If I put this one here, the other group will be here. Yes or no? On the 3rd position. If they are to be trans, is it going to be the wedge or is it going to be the dash?
The dash.
The dash, okay? So if you put this here on the wedge, for this to be trans, the other group has to be here. Because they are on opposite sides. And that shows you, if you put them both in the dashes, that means they're on the same side.
They're in cis.
If you put them on the different ones, that means opposite. I don't know about you, but I think we're done with these cyclohexane things, yes? Are we done with these constitutional isomers too? Let's go into acids and bases. Before we go into chirality. Acids and bases is what chapter? Chapter 4? Now this should be easy for all of you. Because you had 1046, yes? From what I remember, I'm not sure, we had 3 definitions, yes? For acids and bases. Three definitions. One was called the what? Arrhenius. And the Arrhenius said that if the concentration of H plus goes up, this is called an acid. And if the concentration of OH minus goes up, this is a base. So these bases necessarily need to have what? Hydroxide in it. Yes? No other bases were allowed under this definition, so they came up with Bronsted, Lowry. And this definition was about proton donor is an acid, so still gives away H plus, yes? And if it is a proton acceptor, it is a base. How do you spell acceptor? With an E or with an O?
A-C-E-T-T-O-R. O-R.
Is an O?
Yeah.
Good. Some of you speak English. So now these bases, you can have bases like ammonia. These bases don't have hydroxide in it. Like these needed to have sodium hydroxide, potassium hydroxide, they needed to have hydroxide. These bases now do not need hydroxide, they just need a lone pair. And this lone pair is going to act like what? like a proton acceptor. Yes? And then we have the Lewis acid-base definition, and the Lewis acid-base definition are about what?
Electron acceptor.
This is an electron acceptor. And this is,
Electron donor.
I should say, electron pair acceptor. And this is an electron
Pair donor.
pair donor. Okay. Lewis acids and bases are the ones that have incomplete octets. Write it down. I got tired. Lewis acids have incomplete octets. Transition metals. And in general, positively charged. So, is that a Lewis acid? This here? Is this a
Yes.
Lewis acid?
Yes.
This acid is a Lewis acid. Is it a Bronsted-Lowry acid too? Yes. And is it an Arrhenius acid? Yes. How about this? AlCO3. Is that a Lewis acid?
No.
This is a Lewis acid because it has an incomplete octet. Aluminum has 3 bonds when it's supposed to have 4 because it does not have a complete octet. It has 6 electrons and it's supposed to have 8. So this is a Lewis acid. Is this a Bronsted-Lowry acid? This? No. It doesn't have a proton to give. So this is only a Lewis acid. Not a Bronsted-Lowry, not an Arrhenius acid. How about this? Best friends, 3 times. You guys don't remember when I said this in 1046? Shame on those that don't remember. Only up to 3 times. So, why is this a Lewis acid? Because it has an incomplete octet. And something like this is also a Lewis acid. It has a transition metal in it. These are only Lewis acids, and they are not Lewis acids under any of these definitions. So on the test, I may give you a whole bunch of acids and ask you which of the following is only a Lewis acid. What's happening?
Bless you.
Who's having problem breathing? You hyperventilate? Okay? Yes? This is something you have to know, okay? So a Lewis acid is a what? Let's say this. This is a what? And what does it like to do? It is an electron pair acceptor. So if there was something else here, like something like this, or let's say something like this, does that have electrons to give to something else?
Yes. Yes.
It's not going to give them away forever, but it does have electrons. And electrons tend to do what? To go to things that are missing electrons or positively charged. So this would work like that. The electron pair will go to that aluminum, and this will look like this. Al, Cl, 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 and now the oxygen Write the charges for that. Write the charges for aluminum and for oxygen. Formal charge.
Oxygen will be
Negative.
positive.
Oxygen, negative.
Oxygen will be positive.
Positive.
Yeah, because
It has
if you
three,
got-
yeah, Well, positive. you have
Yeah,
one,
positive,
negative,
and
three.
aluminum.
You did this
You have
already.
5, so it's gonna be a One, negative two, 1. three, 4, 5. You have 5. So you have
What are we gonna do? You like the finger?
Lone pair.
You wanna do the finger test? Or no?
6 minus.
Oxygen has a valence of
6, yeah.
6, yes? Minus, okay. 1, 2, 3, 4, 5. Oxygen is positive 1. And aluminum is where in the periodic table?
3.
3 minus 1, 2, 3, 4.
Yeah, negative 1.
This is minus 1. So this aluminum is minus 1. You are going to have from 6 to 10 problems on the test on determining formal charge. You should be able to do this in a split second. Yeah.
Can you repeat that last step one more time?
Which last step?
The
formal charge?
Yeah, yes, sir.
Yeah. Well, we're using this technique that I came up for you guys, which is called the finger, yes? Valence, how many valence electrons? 6 for oxygen, because oxygen is in group 6. And then you just count with your finger bonds and electrons all the same. 1, 2, 3, 4, 5. Yes? 6 minus 5 is plus 1 for the oxygen. The aluminum is in group 3. 1, 2, 3, and 4. So 3 minus 4 is minus 1. Conjugate acid-base pair. HCl plus H2O is going to give you what?
Hydrogen and chlorine.
Hydronium. Let's say that this is an equilibrium, okay? This is going to act like the what? Like the acid, and this is going to act like the base. So this is the acid, and this is the base. So this will become H3O plus Cl minus. What is this Cl minus called?
The conjugate base.
Conjugate base. Most things that are negatively charged or have an electron pair are bases, yes? And so this is the conjugate base. Most things that are positively charged are acids, so this is the conjugate acid. I expect you to find what the conjugate base and the conjugate acids of things are, like you did in 1046, but I don't want to review this, okay?
Okay.
Because I got tired of doing this already. Okay, you'll make that with water, act as an acid, and in another equation, acid-base. Write both equations, that as an acid, and this as a base. That's both. So in one, this will be the acid, and in the other one, the base.
Can you read what you wrote?
What do you mean, read what I
The
wrote?
computer
H?
is like,
The computer's in the middle? Oops, whose cell phone was that? I broke it. Okay, if this acts like the acid,